Hello students, we're going to look at the Edexcel, Pearson Edexcel Computer Science GCSE Paper 1. This is the 2020 spec 2022 paper in preparation for GCSEs. So it's really important when you're doing exam questions that you fill in every question, answer all the questions, use the space provided. There are no calculators at 75 marks out of 150 for the total GCSE. And let's have a look. So, do read the instructions, use a cross, make it really clear what your answer is. So networks, devices are connected to networks. Give 2 reasons for connecting computers in a network. Well, it's a fairly easy question to start off with. I think the easiest would be to share files. That would probably be the easiest. To collaborate, you could say, share peripherals. Peripherals like printers. That would be a good one to have in there. Connectivity, internet connections. So there's plenty you could add in there. So I put to collaborate. Should be a nice easy 2 marks to start off with. Describe one way a local area network, LAN, is different from a wide area network. Well, you might typically have a WAN that's got lots of LANs connected to it. So these LANs are smaller. Okay, they cover a smaller area. So smaller geographical area. So a LAN occupies a much smaller space. They could also be, for example, this could be like a Cisco hardware, and then this could be, I don't know, TP-Link, something like that. So they could have different infrastructures, different manufacturers, and that LAN connects individual devices using switches. So hopefully you study your network topology, star, mesh, and bus networks. If you've got, say, a star network, you've got that switch in the middle, all these computers connected to it. It's very typical. Your kind of router sort of acts like a bit like a switch. So the LAN will use individual devices, switches, whereas a WAN, wide area network, uses gateways. Okay, there's loads there. I mean, there's plenty for 2 marks. Okay, so just to give you context here, because obviously we're revising. A network speed has 17.08 megabits per second. Now it's important to remember that these are bits per second, not bytes. Okay, and a mega, you just need to remember that a mega equals a million. So you've got 6 zeros, haven't you, for a million? So as long as you know that, then it should be a bit easier to say, okay, well, that's the one that's essentially the equivalent of 6 zeros, because we've got the 17 here, and then we've got the 6 zeros. That's the way I remember it anyway. Mega, just remember, mega is a million. And so network speed's always measured in bits per second, not bytes. So we might get a speed question later, we'll see. Define the term latency. Right, well, latency is to do with the delay, between data being sent and it received. Between data being sent and received. Data is split up into packets for transmission over a network. Each device on the network has a unique identifier that is used when sending or receiving packets. State the name of the unique identifier. The easiest one to remember is IP address. But technically also every device does have a MAC address, which is nothing to do with Apple Mac. It's just it's a hardware identifier. So your phones, iPads, everything, they all, but PCs, Windows computers, they all have a, sometimes it's called Wi-Fi address for some reason. It's a MAC address, and that's a unique hardware identifier which can also be used sometimes. But that's the easiest answer, IP address. Identify the item included between the header and the footer in a data packet. Well, this is a bit of a weirdly worded question. In the header of a data packet, you're going to have this sort of the destination IP address, the sender's IP address. You're going to have like the packet number. You're going to have quite a lot of information, but in the middle, you're going to have the data. Okay, so the data being sent is what they're getting at here. All the destination stuff and the key and the packet number are not in the actual data itself. So just, if you've got a picture and you're sending it across the World Wide Web, it's like chopping it up, a bit like a jigsaw. You chop all those pieces up, and they've all got little, they're all going to fit together, but they're all going to given like a number. That's going to be number one. That's like this piece here, and it's going to have where it came from, where it's going to, and what the order is, plus other metadata. Describe how a firewall protects local area networks. Well, firewalls work. Firewalls, they monitor traffic all the time, like they're constantly on, and so they use a set of rules, okay, and it could be a list of, let's say, authorized computers or IP addresses. It can also, how it will also work is to have what we call ports open and closed. So you can have, let's say, port 80, which deals with Apache webs. Port 80 is for web traffic. You can turn that on and off. For example, if you didn't want it to the web server to access the internet website, any sort of World Wide Web protocol, HTTP. But these are the safest options there. State the name of an email protocol. Well, there are two. IMAP's the most widely used one, but we can also have POP3 because before devices were better with internet's connection speed, bandwidth, and with cloud storage, people used to use POP3 to download emails directly to their device, and then it wouldn't be on the server. And sometimes you might use that for security reasons. But IMAP's what pretty much everyone uses now. Explain one disadvantages of using a star network. Well, we actually had a little look at star networks. And if we look back at this, the one I drew earlier, if this switch fails, then all the devices will stop working. Okay, so you've got all of these computers, and they're all connected, sort of like a star shape, to a switch, which handles all the traffic. So if that fails, then that's going to cause a problem. You could also say they're more expensive to set up, cost more pounds to go up, and it needs each device needs a cable to go to the central device. A few things you could say there. Also, it's limited. Like the switch can only handle so many computers at any particular time. Let's have a look at the next question. Computers, some low-level programming languages use mnemonics. State the purpose of a mnemonic. Well, so I mean, you'll know these, like BIDMAS, for example, or SOHCAHTOA. These are all ways to remember things, or every good boy deserves a favor. Brackets, indices, division, multiplication, addition, subtraction. So in the context of this, we're talking about assembly language, which I'm just answering. It's the second question here. So I'll state the type of low-level program that uses mnemonics. So what is the purpose of them? Well, for an assembly language, it's instructions. Their instructions makes instructions easier to understand or read. They're actually human readable. I mean, there might be something like load or add. You know, in fetch, decode, execute, you might have like load 5, add 6, or something like that. Load location 5, add location 6, something like that. And mnemonics are one characteristic of some low-level languages describe another characteristic. Well, there are lots that we could put in here. Machine code is the lowest level, is written in binary. Okay, so that's the lowest possible level, and those are going to be all the zeros and ones that pertain specifically to a particular manufacturer, like HP or Dell, or something like that. They're also hardware specific. So assembly language is a low-level language. In fact, in terms of the Edexcel GCSE, the only two low-level languages are machine code and assembly language. Those are the only two. They're hardware specific. So I'll write that down. Hardware specific. And they can be highly optimized. So all those old Mario games and Sega sort of Sonic games were probably originally written in assembly because the hardware was so limited. They had to squeeze everything they could out of the hardware. Okay, state the name of the high-level programming language translator that executes a line immediately after translating. Okay, well, an interpreted. So Python is an interpreted language, whereas something like C is a compiled language. So there are different types of translators. There's an assembler, compiler, and interpreter. So here it's asking you to remember what high-level language uses that to translate. State the two items held in RAM. So data or instructions, we just saw that earlier. I think if we fetch, decode, execute. If we've got data, we might have just like a 5 here. Or an 8, let's say that's an 8, and that's location 5, something like that. So it could be data or instructions. Now let's carry on. Data can be stored in different ways. Describe how data is stored on optical media. Well, optical media, for example, a CD, DVD, or a Blu-ray, has a reflective layer on it, and on that reflective layer you'll get essentially lands or pits representing, so lands and pits represent binary ones and zeros. So When the laser looks at those, there'll be a slight delay in the bounce back from the laser. If the laser's sort of pointing up, there'll be a slight delay because it'll take longer to travel. And of course, that's read very, very quickly, and that will know if it's a 0 or a 1. State the type of secondary storage that stores data as electrical charges. Well, solid state disks do that. The other one would be magnetic. If you've got an HDD magnetic storage device with a spinning platter on it, that will be a magnetic coating that will hold those zeros and ones. But the one that holds electrical charges is an SSD solid state. Similar to your USB sticks. Let's carry on. Here, an embedded computer is part of a larger machine. State 2 characteristics of an embedded system that make them different from general purpose computers. So it's important to note that sometimes embedded systems, they contain chips which might be used, like especially in the 80s. There was a very famous Motorola chip that was used for basically everything, from general purpose computers to single embedded systems as well. However, embedded systems usually have one single task. Now you've got to be careful. I don't think they want that as the answer here. So better answers would be less CPU, processing, or memory. We could say limited memory, lower costs, they'll be smaller. Think of your webcams or something like that. That might be security cameras. They might have a very limited user interface, or a washing machine is also a good one, isn't it? A washing machine is an embedded system. It's got all these functions in it, and it's not being used as a general purpose computer where we can load different programs on and run them. All right, identify 2 reasons for data compression. Best answer, well, 2 reasons. So they reduce data transfer times when you're sending. If you have a load of files and you select them all and you compress them, let's say it's a zip, you are going to reduce the size of that. So it's going to reduce the required storage, and it's going to take less time to transfer. It definitely doesn't reduce the chance of being hacked, and error detection and correction out. It reduces different out. So the A and C are the only common sense answers there. Robust software must be free from vulnerabilities before it is released to users. Well, tell Apple and all the other companies that. Programming bugs are one type of vulnerability. State 2 other types of vulnerability. So, there are all sorts of things here. Security vulnerabilities. There could be, we've got so many. We've got insufficient testing. Or, lack of data used to train software, something like that. Weak design, poor design. Those are probably what I would go with there. Some users are given administrative privileges. Explain one way an operating system allows an administrator to manage users. Well, just think of your context at school. How can the IT department or your teacher administer? They can add users. Users can be added. If you're an admin, you can add people, or delete it for that matter. You can change their names. You could edit permissions. So you do want to link these together. So you could say users could be added or deleted. So we want a linking word. People can use the same computer. All right. So that would be a mark. That would be a mark. When you've got these command words explained, you want to link this explanation together. Data, computers manipulate binary patterns. Convert the denary number 57 to an 8-bit binary. Okay, so it should be pretty straightforward for this. We simply, if you're in doubt, we've got 2 to the power, sorry, let me make that tidier. 2 to the power of 0 is 1, isn't it? 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 times 2 times 2, 8, 16, 32, 64, 128. All right? So if you really can't remember, you can write out 8 bits, which is 1 byte. And then for a 57, we don't want that one. We don't want that. We do need a 32, don't we? We need a 32. We need a 16 because 32 plus 16 is 48. And what we're missing is 9. So we just need the 8 from here and the 1. And that's the best way to work it out. Literally write it out and test it and make sure it's done, because you'll probably get because 2 marks, you get a mark per nibble. Convert a binary number to so 00101101 to hex. Now notice how I split it in 2, because this is the trick. 8421, 8421. That's a 2. That's 8 plus 4 is 12, 13. Now A equals 10, B equals 11, C equals 12, D equals 13. So you'd write D here to D. So to find hexadecimal, you just split up into nibbles and you look at each one, 8421, and then you represent it. So 1 to 9 is as normal, E is 14, and F is 15, isn't it? So you get 0 to 15, 16 values hex. Describe the process of converting a binary number to 2's complement. Well, you flip the bits and add 1. So let's have this number up here, this 57. Let's do that. So if we wanted to represent, I don't know, minus 57. So we've got 0 0 1 1 1 0 0 1. Flip all the bits and add 1 to it. So 1 at the end. And now what we have is this number, and even though in the specification for Edexcel they don't say you have to know about the MSB, the most significant bit, I think it's worth knowing. So this MSB, that this one here, is worth minus 128, and all the others are going to be positive numbers, and this is how we build the number back up again. So we've got a 1 here, 0 0 0 1 1 1. So we start off with minus 128. Then what we do is we add 64 to it. So we've got minus 64. Then we add 4 to it. So we've got minus 60. Add 2, we've got minus 58. Add 1, we've got minus 57. So we've just proved that the number that we're representing here is indeed minus 57. Just as an example, this will help you if you've got more complicated Two's complement questions, you can always check it, and it doesn't matter if you've just got a nibble, like say you've got 8, 4, 2, 1, 1, 1, 1, 1. If it's in two's complement, that's going to be a negative number. So what is this? -8 plus 4 is -4, -2, -1. This is equal -1 in two's comp. If it says in the question it's in two's comp, then a nibble like this would be, you can do it from any amount of bits. The one on the left is always negative. Explain what has happened as a result of adding these two 8-bit binary numbers. 9 times out of 10 it will be an overflow error. So let's have a look. 1 plus 0 is 1, 0, 0 is 1, okay, 0, 1 is 1, 0, 1 is 1, 0, 1 is 1, 1, 1 is 0, carry the 1, that goes 1 goes down here. 1, 1 is 0, carry the 1, because 1 and 1 equals 2. And to represent 2 in binary, you have to have 2 bits, don't you? On 0. And that's to represent 2. So that's why you carry the 1. Same with 3. Like if it was a 3, you had, let's say you had 1, 1, and 1 together, then you'd put a 1 into the column and then carry the 1. That's the trick that I tell my students. So we can't, we've got 9 bits. The only way of storing this is, so we can say not enough bits to store result, 9 bits needed, an overflow error has occurred. Okay, it's more than enough. As soon as you mention things like overflow, the examiner knows what you're talking about, and you know that there's a 9 bits here. After applying compression to apply, the original contents cannot be constructed fully. So this would be like an MP3 or a JPEG. You cannot restore the original file from those. They're lossy. So you've lost information forever. It's gone. There's no way you can get that back. The other one is lossless. Okay, if you had lossless, like a PNG file or something, or a logo, then you're not going to lose any information. You're not going to. You can restore everything. But lossy, like an MP3, you can't get the original audio file back that's got the highest quality. You've lost information. MP3s are about 1/10 of the size of the original sort of WAV file. Data can be encoded using ASCII. Yeah, it's an American standard for character encoding, and describe ASCII. Okay, fine. So it's a standard. Just remember what that S stands for. Standard used to represent characters, data, or I'll say characters, text. I think that's better. Text, characters, or text, and it allows other computers, because that's why it was made, so all the computer manufacturers can have something that works across the board to use same data, I guess. And ASCII is in 7 bits. The original ASCII is 7 bits. Sometimes you get exam questions for that. Extended ASCII is 8 bits, but the original one is only 7 bits. So the leftmost bit was saved for other computer information, because most computers were only 8 bits when it was implemented. A pixel is the smallest element in a bitmap image. 2 images are displayed. Okay, so this is like, just out of interest, HD and full HD, 1080p. One reason why the second image will be displayed in more detail. Okay, well, it's got a higher resolution, So you could say the density of pixels is higher. There's an idea called pixels per inch, which isn't very clearly explained in a lot of revision sources. So you can, for retina displays, you technically have like over 330 ppi, pixels per inch. So you can have an image with the same pixels, but with a denser count. So it's not a very clearly worded question here, and also the revision isn't great for this. But essentially, there are more pixels. Okay, so there are more pixels, more highly dense. You can say the number of pixels per square inch is higher. A 10 color bitmap image uses 15-bit color depth. The image is 1028 by 640. Complete the expression to show the minimum file size for the image in megabytes. Right, okay, so we've got to be careful here. What I would do is always just memorize KIB, MIB, and GIB. Just memorize it. So 1024 to the power of 2. These are all base 10, aren't they? Power of 3. If you had 2 to the power of 10 equals 1024. Like 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, 2, 5, 6, 5, 12, 1024. Memorize that, and then you can also say this is 1024. Oh, hang on. 1024 times 1024 is another way of saying that. Okay, that's another way of saying it. So here, if we times 1024 by 1024, that's going to give us our megabyte. And when we're dealing with bits, we have to make sure that we've got an 8 on the denominator here, because there are 8 bits in a byte. And the formula for image is width times height times bit depth. So the bit depth here is 15, and the width is 1028 and 640. So there are 4 marks there. You'll definitely need to remember this to get a mark, and remember the numerator. This 10 doesn't really feature in there. It's a bit of a red herring potentially. Issues and impact. Explain one reason why files should be backed up regularly. I mean, use a little bit of common sense. Helps data loss, quite frankly. The easiest answer. We could say, I mean, that could be a mark, because you have to link this together, because let's say malware, malicious software could delete data, or let's say data could be accidentally removed. I think that's a very safe answer there. You can restore your data if there are physical hazards, if there was a fire or something like that. Water damage is typical, isn't it? So backing up your data is highly recommended. Consent must be attained before organizations can use personal data. Give 2 pieces of information that organizations must tell people. They technically must tell you that there are loads of things. You have they have the right to refuse. Right, you have the right to say no. How long data is stored. That the data should be stored securely as well. It should be stored securely by the. I mean, we had problems with obviously Co-op and Marks and Spencers recently. Um, they they lost lots of data, so I mean, they should have put more efforts in to secure it. Um, that you can withdraw consent. You can withdraw consent at any time. You should, and technically, you're meant to be able to see the data itself. I think my camera feed's just gone. Anyway, not to worry. Police forces use algorithms to help. Look at 6 marker here. How many officers are deploying, where to send them? Discuss how algorithmic bias can affect the decisions police forces make. Your answer should include bias, impact on individuals. So it's all about algorithmic bias. So algorithmic bias is usually to do with machine learning, AI, large language models. So we could say, I'm just going to abbreviate this a little bit. You could say insufficient data, or inappropriate data used to train the model. So you could also have human bias. So it leads to discrimination, for example. And of course, humans are creating these algorithms. The algorithms are going to be an extension of humans in that regard, and their thought. You could have deploying officers to the wrong areas. So we could have in communities with algorithmic bias, deployment to wrong areas. Individuals feel monitored. I mean, this is happening quite a lot recently, isn't it? Or targeted. Or unfair treatment, discrimination. It could be particular communities. Discrimination can happen in all communities, including white British. Feedback loops. We could have human oversight. So how could we reduce the risk? How can we reduce this? More human oversight and management. So sort of checking, sense checking. Governance. I'm going to put government. So things like AI you'd want, or social media. Recently, the government are trying to put more legislation in place. Improve training data. So I think there's more than enough for 6 there. Just sort of break it down. Try to go for 2 here, 2 here, 2 here. That's the safe option. And just tick them as you go. Have I written 2 things for each one of those? If you've got a big 6 marker. Computational thinking. Here is an algorithm that prints colors. Let's have a look. State the data type, or type of data structure that holds the ink colors. Well, it's here. It is technically an array, Python nest. Arrays are implemented as Python lists, so do our records mostly. But in other programming languages, arrays, well, actually, some programming languages don't allow you to have different data types. Python allows you to have the same data type. Give the contents of int colors 2. All right, well, int colors index 0 is there, 1 and 2, so yellow. Always count in Python, and most programming languages, we always count from 0, index 0. State the name of the computational thinking technique used by the subprogram, display all, to hide the logic of printing abstraction. Because subprograms, subroutines, they're both decompositions and abstractions, because you can use them to break down. I'm sure this one's to do with decomposition. Yeah, used to break to different blocks, break it down. Decomposition. When we break it down, we've got a big problem. We break it down into smaller steps. That's decomposition. To hide complexity and logic and focus on the most important stuff is abstraction. Think of the London Underground map. Think of the London Underground. It's not got all the bends and all the other stuff that's actually underground. It just is an abstraction of what's there. This algorithm searches for a sorted number, an array of sorted numbers for a target value. The target value may or may not be in the array. Use of the found variable to help make it more efficient. Okay, well, it's similar to how you might have probably bubble sort or something like that with a swapped flag. So you could have. So let's have a look. This is just part of an algorithm. While the index is less than the length of the array and not found and not passed. And by the way, all of those have to be true. All of these have to equate to 1 or true for the condition to carry on. If the array index does equal the target, found equals true. So if found, it's very likely up here found will be given a false value. So not found would be true. Not false is true. That's why this while loop probably carries on. However, if this part works, then found equals true, and not found would be false, which would stop it from running. So if the pass through the loop goes past the expected location of the target value, if pass through loop goes past expected location of target value, the third condition for the loop will not be met. I'm just abbreviating here, will not be met. So you could also say if the value of the item at the current index position in the array is more than the value of the target, no more passes of the loop are required, the loop will exit. So it's a way of stopping the algorithm. That's what all these questions are going to be related to. It's a way of stopping the algorithm early if we need to. Laura owns a fruit shop. This program checks the weight of boxes of strawberries. Okay, fine. So this is probably leading to a trace table. We'll have a look. Count these. So these are all it's typical in Edexcel GCSE that they assign values, default values, in your global variables. Constants are written in uppercase. Global variables usually are given a comment. Global variables which can be used anywhere in the program. So while count is less than 4, so count is less than 4 because it's 0. So we'll have 0, we'll have 1, we'll have 2, and we'll have 3. So we just got to keep that in mind. Count equals count plus 1, so we increment count every time the while loop goes round. Weight equals integer, so we're converting whatever they type in, the weight of the bot, into an integer, because the input statement is always a string. If the weight is less than 395, or, so with an or, if you've got two inputs, you only need one side to be true for the output to be true. Okay, so only one of those sides needs to be true for you to actually have the whole statement go through. So if the weight is less than 395 or it's greater than 405, reject. We add 1 to reject. So what we were saying here is, okay, what's going to happen? So first of all, it would be 0. And then let's have a look. The inputs are 404, 393. So we're going to start off with count being 0. And then they're all, these to start with are all being 0. They're all 0. And then next, the we're going to have count as 1, and we're going to, the weight is being given as 404 because the count gets up. Remember, the count gets updated first. So 404. In fact, you could probably save time and literally just put these in order. And we know that we're going to get to well, let's just keep that there. Let's do this. So count except is 404 the weight. It's a reject, isn't it? So, oh, hang on. Let's just check. No, sorry. 404. So if the weight is less than 395 or it's greater than 405, then reject. Else, accept. So 404 is accepted. So we can say accept. Okay, I think we're fine here. Then count is 2, and we've got another, the input is 393, so they enter 393. Let's have a look at 393. So 393 is less than 395, so that's a reject. Then we've got count 3, and we're going to count 3 is 395. So if it's less than 395 or greater, so it's also so if weight is less than 395 or it's greater, well, it's neither of those, so we don't count that, we go to accept. So it's another accept. So now our value for accept equals 2, doesn't it? So at this point, what's going to happen? We've got 0, 1, 2, and 3. 3, 9. We've got how many? 405. So the count is still 3. So this will run one more time because count at the moment is 3. So when we run it the last time, the count is going to increment to 4. So that means we're not going to run it again. Count goes to 4, and we've got 405, which will be an accept again because it's not greater than 405. So we've got a 3 for accept. And then finally, Once the loop's done its thing, we've only got one print statement, accept, reject. So we just want to write out what would it be, and the display would be 3 and 1. And what most students will probably mess up here is they would probably put displays in here, and they would probably get confused about the last count. So that's a 6 marker, and we've got to be really careful you've got to be very careful. The count gets incremented as soon as the while loop's actually running. An algorithm flowchart question, by the way, if this ever comes up, that's a sub-program. Informs the user which number is greater, which number 2 equal. Okay, so the algorithm then enter 2 numbers and then which one is greater, and we want to represent it as a flowchart. So draw a flowchart to represent this. Okay, so you've always got to have start, and you've got to have an arrow, you've got to have the direction. We've got input to the system, so we always use a parallelogram. So input number 1, right? Then we've got to do another one. Input number 2. Then, once we've got the 2 numbers, we need to make a decision. Is num1 does it equal num2? Is it the same? So that either no or yes. You do label them. Do label the axes here. Always yes and no. Don't just put true and false. Sometimes you can get away with true and false, but always label the arrows. So if it's yes, we can display equal. Okay, because they're the same. And then we can stop the program, can't we? Always have these terminators. There's always a mark there for terminating it. Now, if it's a no, we can have other decisions to make. Is number 1 greater than number 2? You know, it's either going to be yes or no. So I'll put yes here. Let me tidy this up. Or no. Okay, and then is it going to be less? Is number 1 less than number 2? Well, actually, we don't need that at all, do we? We can simply say, because we've just checked all the permutations already, haven't we? We can just say display num2 greater, and then that can go to the end. And then here we can say display number 1 greater. Okay, so rhombus are decisions, parallelograms are inputs or outputs, and we don't use any processes here. There's no processes needed. Nice 6 marks. I think that was a 6 marker. There you go. That's it. That's the paper. Okay, so I know I put a lot of information into that, and hopefully that helps you when you're going over it. But unfortunately, you just got to do the hard work and know your stuff when you go in. All right. Good luck.